So just I decided to, I think not everyone has been in the last lecture, so you're a bit confused what has happened, I think, some of you. So I had put here in the binder, I put here, so that was the first and second class, traditional class with lecturing and recording and notes. Then we had one session where we had, where is it? Okay, so we still had 3 classes, regular lecturing. And then we had one class where we had this group activity. Okay, that was actually last Friday, I think, right? And here we also made a quiz in class. I'm going to paste it here, so those of you that could not come also know what I forgot to paste it. And last class we were supposed to cover some theory, okay, but the presentation took a bit long. So these are the people that have presented so far. If there is any mistake with the name, just let me know, but that's what I wrote. And we had some short discussion on water disposal using water injection, and we also had a brief recap on the analytical development of field production profile for an undersaturated oil reservoir. We had a brief discussion on that, and we didn't have time to do more. So I say that for the people that still have to present, I think we have like 4 or 5 groups left. Let's take it next. Those of you who prepare for today, I'm sorry, but if we can take it next week, okay? So we take all of that in one group in one day. Probably will be on Friday, okay? But remember that you have to, you have to present here in class. The evaluation will be made based on your presentation, okay, of the exercise. But you have to present here in class for us, to start evaluating. Okay. Yes?
So we should still submit the PPT on Sunday?
Yeah. Everyone should submit the PowerPoint on Sunday. Okay, so today I want to go, so the idea is that we are discussing now very much, we are focusing on one crucial aspect of field development, which is trying to compute, trying to characterize, trying to predict the performance of the production system. That's what we are doing right now, and we are going to spend a few more time on that, okay? Because it's crucial. That allows you to compute, to decide first. You can decide. You can say how much I want to produce, but then it also allows you to predict. After I cannot produce what I want to produce, what will be the production? Okay, so it's basically planning the production scheduling, the production profile, and predicting the production profile. Okay? We started with 2 simple cases, just using the reservoir, just using analytical equation, but now we're going to increase in complexity, and that's the plan now. We're going to increase, make it more and more, gradually more and more complicated. So today we're going to talk about the rest of the system. If you take into account the whole system, it will be slightly different than what we have discussed so far. Then we are going to talk about, the plan is to talk about network, when you have a system that is not only one well, but you have multiple wells. Then we are going to discuss some considerations for when you have oil-gas systems. We have been discussing for only oil and only gas, and then we're going to go for both. And the last part will be what happens when we have boosting. Boosting is becoming a more frequent or a more common strategy to be able to produce more from the reservoir. So we want to see what happens with that. And then after that we are finished. We have most of the tools we need for understanding field performance. Okay, but this is the work we are going to be making in the next week. Also, we are going to have some, and that I will see where to put it, but we have to see at the end is not only how much the field produces or the recovery factor, how much oil I produce, but it's actually have to translate that to revenue, to profit. Okay? And for that we use an indicator. You have probably already done it in your exercise. That is the revenue, the discounted revenue. But we want to add also to that the expenses. So we have to sum all up in the same reference, expenses and revenue, and that gives me one compound number over which I take a decision. Okay, so that number is very positive, very big, NPV, net present value. That means that that project should be very profitable, and I'm more willing to go forward with it. If it's very low or even negative, that's a strong indicator that I don't want to go forward with that project. Okay. So let's look at something that is called flow equilibrium, and we are going to look at the particular case of dry gas. Dry gas, first we have in Norway, the gas production is very important. Actually, most of the fields producing now, they're already producing so much gas that they can be considered gas fields. But we have giant gas fields like Ormen Lange and Snow White, and gas is more strategically becoming very important. But not only because of that, but also because we can have, you will see now, but we can have analytical equations for the whole system. When we go to multi-phase, when we go to single phase, it's a bit difficult to have just one nice equation that we can use. Okay, that's also the other motivation why to use dry gas. Okay, so now let's see at this diagram, and we have here a production system going from reservoir, okay, a dry gas reservoir. We have flow towards the bottom hole, and that's where we stopped last, or in the previous examples. Okay, at this point we call it the bottom hole or the bottom of the well. Okay, but this point of pressure we call it the flowing bottom hole pressure. So from PR to P, let's try to make here a diagram. From PR to PWF we have flow in porous media. Okay, that means flow in the formation. For that we have, you already got a taste, right? We use something called IPR when we can. Okay, inflow performance relationship. Okay, and the value and the equation that we use, we said basically, well, we can take out the time from that equation, which is very helpful. If we take time out, then we can get some equation for liquid, for oil, undersaturated oil. It was J times PR minus PWF. And for gas was what we call the backpressure equation, C PR squared PWF squared to the power of n. Okay, because time, we could take time out. These are in PSS, that stands for pseudo steady state. The only effect on the depletion is when reservoir pressure is reduced. Time is not on that equation. Now, something that we didn't discuss that is very important is how that equation looks like and how that equation is plotted. So for oil, for undersaturated oil, and note here, this is the rate at standard conditions. Okay, it's not the rate at any local place. It's not the rate. It's the rate at standard conditions. So it's like a mass flow. It's like a modal flow. Is equivalent to that. So if we make for liquid, we usually say PWF, and it should be a straight line. Let's make it less productive. It was too productive that well. Okay, it's simply a straight line. That means if I impose that pressure on the sand phase, that's how much the reservoir will produce. Okay, and that makes sense, right? If I lower that pressure, if I'm able to put there just to put vacuum, okay, I will get more and more rate out of the formation. So intuitively, it makes sense also. So that's for undersaturated oil. Okay, you can also use it for water injection, for example. water injection. And then you have the back pressure equation, which looks slightly different. So, sorry, what is this point here? The intersection on the y-axis? Reservoir pressure, right? When I have no flow, the pressure should even out after some time, and the pressure I have here should be the same as the pressure I have there. Simply reservoir pressure. Now, for the gas, it looks curved. Looks something like that. If you go and plot this equation, the back pressure equation, you should get here PR, sorry, let's make it like that, PWF, and that point is PR. And that's basically, it gives it a non-linearity to the equation for gas. And remember, also this equation was for low pressure. When we go to medium pressure, high pressure, it looks slightly different. But we are working with that equation because it's very convenient to use. That's how the IPR equation looks like for dry gas and saturated oil. And also saturated gas. That means any case where I have some compressibility, some effect of density variation with pressure, basically the properties are changing with pressure of the fluid, the curve is going to look curved. Okay, it's going to look nonlinear. And you can go to the literature, you can spend a month, a lifetime looking at different equations for all kind of cases. Okay, horizontal well, vertical well, deviated well, slanted well, slightly light oil, heavy oil, all kind of things. But you have to keep in mind two things. If time is not in the equation, pseudo steady state, I assume the transient is very fast and all the rest of the outtake happens at that regime, and no compressibility, a straight line. When it's some effect on pressure, you have a curve. Okay, now let's go and continue forward to see what do we find. And we find one thing, right? We have flow now on through a pipe, right? From bottom hole all the way. We can actually, make it any place, but let's go all the way to the wellhead. So that's the wellhead pressure, what I have here. Okay, and just a short comment. At the well, we have a collection of valves that are basically what we call the tree of the well. And we have some valves that are for, anybody knows what these valves are? The lower one, master valve, that's the one I use if I want to close the well for some time, okay, completely. Then I have the two wing valves on the side. One of them you produce, the other one usually I have a pressure sensor, and then I have the one at the top, which is to make intervention, okay, the swap valve. So these valves are not typically used in normal operations. They are on and off. It's either for intervention, for closing, but I have one valve which is also on the tree, which is very important, which is the choke, which is a regulation or a control valve. And that we use very actively. You already got the idea from this tank analog. We have to use this valve to regulate production. Okay, so how does the equation looks like when we go from point PWF to PWH? Okay, now we go from PWF to PWH. How does the equation look like? Well, basically, I can use the same. If you think about Bernoulli equation, right? I have a point in a pipe, 1, and then it goes to a point 2. So I say that the energy between point 1 and 2 should be the same, right? So I say, how do I put the energy? Z1 plus P1 over the density times gravitational acceleration plus V1 squared over 2G should be equal to, you remember this equation? I guess it was taught long ago when you were in kindergarten, probably. Basically you're saying, and that some people use H, that's some sort of an energy. You say H energy in 1 should be equal to it, the energy in 2, but I usually have some losses in between, right? And these losses I can use, for example, friction losses. I use a friction factor, the length, diameter, b squared over 2g, right? So I say, if you look at that equation, it's like I have energy in point 1, and then I'm losing energy, which is this guy, and then I end up in point 2. So for gas, we are talking now, that applies very much for a liquid, right? When density doesn't change much, this friction factor, what does it depend upon? Again, you know, going back. Okay, it depends on the Reynolds, something called the Reynolds number. And the Reynolds number depends on density, diameter, velocity, and viscosity. And then you have the relative roughness that depends on the roughness by diameter. So the point I want to make here is that usually in liquid, even in liquid, okay, due to the reduction in pressure and the reduction in temperature, these properties change along the tubing, along this pipe. It's basically flow in a pipe. Okay, we're discussing here is flow in tubing, and tubing is a pipe, or we call it more general, a conduit. So if you see that change, that gives you the impression that you have to make the calculation step by steps. Okay? You cannot do it just in one go, but you have to go and make a step calculation. So I'm not going to go through the whole derivation here. It's also not the point of this course, but I just want to refer to the, you can find it on my compendium. It's one of the appendix, and actually this was written by Golan, Professor Michael Golan. Okay, where you can see the whole derivation. Okay, you start from the general equation, but then now you cannot assume that density remains constant. You have to add something to that. So density is substituted by the real equation, gas equation, okay, and after that you make some integration. Okay, you integrate from point 1 to point 2. So I suggest, let me just take that, and that's in page 133. So I just suggest, you know, on the weekend, you go, before you go to a party or something, you take a look and then see how is that equation derived. Just what assumptions are made. That's page is it 133 compendium. Okay, so you first know that the properties will change, substitute an expression of the property with pressure, because pressure will be changing also. But if you can express that density in terms of pressure, that makes it much simpler. Okay? Then you group factors, then you integrate pressure with the length, and then after a few tricks you end up with this equation. Okay, you end up with that equation. And here we have to make, there are some assumptions that were made that came by deriving this equation. So let me just copy. You have it on the notes, okay? So I'm going just to paste it here. But I just want to make a short comment on this equation. That is important. So one thing you note, okay, the equation has mostly a lot of constants, okay. So you have the pressure at the, that's a wellhead, okay, PT. So I have the pressure at the bottom, the pressure at the wellhead, the two parameters I want to are involved, okay. I have diameter, but here you see I have a few things that I need friction factor, and that stands for the Moody friction factor, and I have an average temperature and an average C factor. And that was because in the integration, by making, you saw the expression before, when I make the integration, I had to make some terms constant. And here I have introduced temperature. So pressure I know is changing, but I assume temperature is not doesn't change that much. Okay, so I can make my calculation assuming that I have an average temperature. And that average temperature will be the temperature at the bottom hole, the temperature at the wellhead divided by 2. I have also, I need, because of that substitution, an average deviation factor. And that deviation factor is the deviation factor at the bottom hole, deviation factor at the wellhead divided by 2. And let's see, S, I also need C average and T average. All the rest are constants. That's the inclination of the pipe. Alpha is the inclination of the pipe with the horizontal. Okay, and then comes this friction factor, which is a big problem, right? That friction factor depends on the Reynolds, and that Reynolds depends on the velocity. However, for gas, luckily, our life is made a bit easier. What is a chart of friction factor versus Reynolds? How does it look like? You have first one range where you have laminar flow, okay? And we are never in laminar flow in gas, okay? And then we come and we have a transition zone and we have something like this, right? Where in this region, from that region on, actually the friction factor doesn't depend at all on the Reynolds, right? What does it depend upon? The roughness, right? The roughness of the pipe. If you see the cross-section of the pipe, you have some valleys, so you measure that roughness, and that will be E, and then you make the relative roughness E by D. So what happens is with gas, due to the low viscosity, due to the very low viscosity it has, and the high velocities usually has, actually gas almost always is on that range. So you don't have to worry about using Colebrook or using all kind of approximation. You just say, well, now I'm in this range. That means that my friction factor is only a function of the roughness, which is a very big saving, right? I don't have to calculate Reynolds, I don't have to calculate density, I don't have to calculate viscosity. And then came one researcher in the 60s, I think he was not a researcher, but a company person. And he found actually that due to the manufacturing process of the pipe, you can make a relationship between this E and the diameter. That means pipes that have bigger diameter usually have bigger roughness. Pipes that have a smaller diameter usually have small roughness. And he was able to go to different mills, to different places where they manufacture this pipe, and actually find a relationship. And that relationship should be someplace here. Okay, Kullender and Smith. That's the fanning, and I don't know if we should have someplace. Okay, but the point is that the friction factor is expressed simply as a function of diameter, because you're in the fully turbulent regime, and also you have expressed the roughness in terms of diameter. Okay, I think it's this expression, but okay, I think that's the expression. We're going to see it soon. Okay, that's the fanning friction factor. Okay, what is the relationship between the fanning friction factor and the Moody? So the Moody friction factor is equal to fanning divided by 4. And voila. That means that that friction factor, that Fm that I had here, that in principle I had to say, well, it's going to change because the velocity changed. I'm saying gas is always in the fully turbulent regime. Therefore, it's only a function of roughness. Roughness is a function of diameter. Finish. And makes it much, much simpler. For those of you that are interested, I think I have a calculator for tubing constant. But we are not going to use it here in class. It's just to show you. So you have all the parameters you need. Okay, that we didn't talk. The equation ends up looking like that. It's the same equation, but generally we make it in a more compact way like that, which depends only on two factors. Remember, the IPR dependent on C and N. Now I have another equation that relates the rate at standard conditions with the two pressures, but now I have two factors also. The CT, the tubing constant, and S, the elevation coefficient. That's a long story just to introduce the equations we are going to use, right? But we have to put some physics. We just cannot trust, where the equation come from. Okay, so it's the same equation I showed before, but basically the equation is QG is CT, that's the tubing constant, P, and here will be 1 WF squared minus P wellhead 0.5. And that's the equation we are going to use. And if you see S depends on the H, which is the height difference between the 2 points. That means the true vertical depth of the formation. I have here this T average that I can say, well, it goes from reservoir temperature to wellhead temperature that I can measure. Yeah. Okay, so here you have a calculator that allows you, I'm going to share the link with you, but here you have a calculator where you can calculate the CT and the S. You provide all of this input, and then you can calculate the CT and the S. Okay. Now, what happens if CT becomes bigger? CT is actually this guy here, right? All of that guy there. So what happens if CT becomes bigger? And bigger means that I use a bigger diameter. If a diameter is increasing, then CT is also increasing. What should it happen intuitively? Should I get more production or less production for the same delta P? More, right? And exactly that's what is happening. If I have these two are fixed, okay, this guy is fixed and this guy is fixed, elevation is fixed, everything else is fixed. So if I increase CT, then the rate should be bigger. If I make a smaller diameter, it should be smaller. Okay, so that's the equation we are going to use, this equation. And we have one more part of the, where we have actually two things in the puzzle here, right? Now to move from this wellhead pressure, we want to move now to the downstream of the choke, right? We are following now the stream, the flow. So we reach the wellhead, and now we have to go through the choke So how do we deal with the choke? What do we do to get an equation for the choke? No idea? We want, remember, now we say, well, P wellhead. We go now to PDC, that means downstream of the choke. And we need for this case an equation. An equation that relates basically the same thing, right? An equation which is a function of QG, is a function of PWH, and is a function of PDC. That's the goal, right? We want to find that equation. Now, so instead of making the derivation, I'm going to show you the ugly equation at the end, okay? But instead of making the derivation, you can find it on the compendium. Again, you have more material to read for these boring winter nights. Okay, but it's on this chapter, chapter 100 and appendix 140, page 140, appendix B. And you can find how the equation looks like. But I don't like these choke equations. I think they are a bit too complex, and they are not very good predicting the pressure drop. Okay, they have very low predictability, because you will see there is a lot of uncertainty in that equation. They work very well if you have single phase flow, if you have gas, or if you have liquid, but if you have a mixture, it's very uncertain. So that's why I don't like to go through the development if it's an equation that doesn't work very well. And that's page 140 in compendium. Okay, but let's look at that in an easier way. Okay, a choke is basically a contraction, and I can have that contraction in many ways. Okay, but I'm going to make it very simple here. In the most general way, it's going to be like a regulating valve, where I have something like that. I pull it up, pull it down, and it's controlling the opening. But in the most general case, I say, well, it looks like that. I also have chokes like that. Okay, these are adjustable chokes, and this is fixed choke, or sometimes call it bean choke. You're saying, well, why are we going so much into? It's important, okay? That's the element that I control my flow of my system. Reservoir guys, they don't want to know anything about choke. Production guys don't want to know anything about reservoir. But at the end, their son, their daughter, the production system depends on both. So both of them have to take care of everything, because it affects the performance of the field. So let's put here point 1 and point 2, and let's try to make a map of how the rate looks like, QSC, and how P2 looks like for a fixed P1. If I have no rate, how should P2 be? Equal to P1, right? If I have no flow through the choke. Now, if I start flowing some amount, let's say this amount of rate, What should happen between P1 and P2? Actually, that's not P2, but that's the delta P. What I'm plotting here is delta P. The pressure drop across the choke. Okay, that means P2 minus P1. So I have no flow, simply I have 0, right? But then I start increasing the rate. How should the delta P be? Actually, again, no, this is P1 minus P2, just to make it positive. So it should increase, right? If I increase the rate, I try to force more rate through that choke, then it's going to increase. It's going to be, the pressure drop is going to increase in a very ugly, non-linear manner as the rate starts to increase. Now, what happens is that at some point, and you will see now very soon how this equation looks like. Maybe we can show it right away. Let me this is the equation. An ugly equation where you have K is the relationship, if you remember from your thermodynamics course, K is Cp over Cv. You have set at the inlet, temperature at the inlet, universal gas constant. All of these are constants. Okay, you have P at the inlet and P2 at the outlet. But it's an ugly equation, okay? Very non-linear, square root. That's why I don't like it, because it's going to make you cry and also going to make me cry. Okay, but you see here it has something, a coefficient. So that means that's taking into account how this equation is derived. Is I go from point 1 and I go to a point at the throat. And due to that contraction effect, the fluid doesn't follow exactly the path on the throat, but actually follows a smaller area. So that CD is multiplying that area at the throat, okay, such that it matches exactly that. So this is an empirical constant to adjust that effect is called vena contracta, to account for contracta effect. Okay. Now, what happens at some point of that choke is that the velocity at the throat reaches sonic velocity on the fluid, right? That velocity becomes, the velocity here, the velocity of the gas at that point becomes so high that it reaches the sonic velocity of in the fluid. What does it mean? That it reaches Mach 1 at this point. Let's say sonic velocity of the gas equal to the velocity of sound in the fluid. Okay, what happens at that point? That's the maximum flow that I can get. Okay, it's already what we call is in critical range. That's the maximum flow that I can get. Q critical. And at that point, doesn't matter how much, if I drop that pressure all the way to atmosphere, doesn't matter, I'm always going to get the same choke. I'm always going to get the same rate. So that we have two very distinct regimes, the critical regime, the subcritical regime, which is from here down, and the critical regime, which is from there up. Okay, and that's because I have reached critical flow, I have reached the sonic velocity. How much is it for air? At standard conditions? 300 meter per second. Okay, so it's a very high number, extremely high number. But in choke we have such as small openings just to create that pressure drop. We want to create a lot of pressure drop with the choke. So therefore we have a high velocity, and that high velocity causes sonic flow, and that sonic flow causes that we cannot go above that flow. So that's why the curve looks like. So to capture this region, I use this equation, and to capture that region, I just have to, the flow will be fixed. Okay? You will be in the critical region. But that's the discussion I had for choke. Do we take a break, or you want to take the pipeline now? Let's take the pipeline and then we take a break. Okay. So now we have from the choke, from PDC all the way to P separator. Can we use the same tubing equation that we were using before? If I say, well, it's an inclined line, okay, let's go back to my, I don't remember, I think we put it fairly horizontal, right? Let's say it will be fairly horizontal. I can use the same equation, it's basically this equation, right? I can probably use the same equation because it's flow in pipe, flow in pipeline, and that means flow in pipe or a conduit, and I should be able to use the same equation, okay, which we had from before. But now we don't call this the tubing constant, but we call it the flow line or the pipeline CP or CFL, and this S we can still call it S, okay, the elevation. What happens if horizontal line what happens in that case? How the equation is changing? What happens with S, if you remember the definition of S? S has the H, which is the height difference, right? If this is 0, simply S will be 0. So let's do that part first. S is 0. Then I just simply have PWF squared minus PWH squared. Yeah, here I'm missing a squared, I think. Yep. Okay. To the power of 0.5. And now what happens with CFL? That was that ugly expression, right? Let's look at what happens in that expression. That expression dependent on S also, right? So all of this remains unchanged. The length, I still will have a length, but now this part is causing me trouble. Okay, S e to the S, ES minus 1. So C flow line is a constant times SES e to the S minus 1, right? If I make S equal to 0, what will happen with that expression? I get error, right? How do I fix this problem? You remember your math also a few years back? What was the trick if you have two expressions that were undefined? L'Hopital rule, yes. Okay, you remember this French strange looking guy, Hopital? That he said if you have that issue, no problem, derive top and down. And then derive once more, top and down. Derive once more until you get rid of that problem. If you do that, then I think that this becomes 1, I think. With L'Hopital, the limit of SES, this tends, when S tends to 0, this will tend to 1. And finally, you end up with the expression, very simple to use, CFL, a pipeline constant. Sorry, that's not PW. Yeah. You didn't tell me. And you will see now why I decided to do it. That's the way we actually make calculations, taking all of these equations, looking at the equation and solving them simultaneously. But I now, after we see that, we are going to go to the graphical method, which I think is much better to understand what's happening. But to make calculations, to get results, you have to go to the equations. But to understand, to my impression, is much better the graphical method. So here we have P, DC, P separator, separator, and DC. Okay? And now we have one equation for pipe, one equation for choke, one equation for tubing, and one equation for reservoir. And we have to see how to mix and solve all of them at the same time. Okay, so let's take a break and we come back to that problem now. Okay, so far we went from formation to bottom hole to wellhead, wellhead to downstream of the choke, and downstream of the choke to separator. We did all of that route. So we ended up with the following equations. Okay, we said IPR, let's count QG, CPR squared, PWF squared to the power of n. So let's create here a table where we say the unknowns and the number of equations we have. So here we have simply one equation, and how many unknowns we have? Reservoir pressure usually comes from material balance, right? Usually comes from how much I have extracted. So this is typically an input. C and N also, if I make testing on the well, if I have an analytical model, I can get a C and N. But I have no idea how much is PWF or the rate. And actually the rate is what we want to find. Okay, so we have here two unknowns and one equation. Next, the tubing equation. Tubing equation was QG CT I think so. Let's check very quickly. I always put the E to the S on the wrong place. And let's see here. Here I have one more equation, one additional equation. And how many additional unknowns I have? The rate, I already had it, right? PWF, I already had it. But now my new unknown I have is PWH. So I have one additional unknown. Yes? So now we have two equations and three unknowns. We need one more equation. So now we go on the choke equation. And the choke equation, we don't know exactly how it looks like, or we know, but it's actually QG, a function of QG, PWH, and PDC. So I have here one more equation, and I have this I already had from before, this guy already had from before, but this guy is a new one, PDC. So it's like this story is never going to end. Okay. Now we go to the last equation, which is the pipeline equation, in where I have QG, CFL, or CPL, PDC, okay. And here finally I have one more equation, but I have no new unknowns. Q was already from before, CP is a constant, this one I had it from the previous equation, and P separator is constant. Okay, remember P separator, I have a control system that is making sure that no matter how much I get, I have oil and gas. Okay, Q oil, I have here Q gas. So I have a control system, first a level, okay, that is making sure that the level is always in the center, in the right place, and also have a pressure transducer that also makes sure that the pressure also remains constant. So that's how the separator, due to this two control system, is always keeping the pressure, the separator pressure, constant. So finally I have 4 equations and 4 unknowns. And 4 unknowns that I have to solve to find a solution, okay, to find the rate. Now I just want to look at it like the graphical, because from the graphical solution we can get a lot of interesting things. So let's see at the graphical solution. You are experts in MATLAB, experts in Excel, so you know if I give you this system of equations, you will find a way to solve it. Okay? You go to your God MATLAB and you say, MATLAB, please solve this system for me, and it should do the work. Okay? But let's look at the solution. And what we are going to make for the solution, I'm going to start to compound. Let's make the production system once more here. And I'm going to start to compound. So we have our well. And this you have to make sort of a leap of faith. Okay, let's see. So I'm going to take, going from the places where I have fixed pressure, I'm going to go downstream, and I'm going to go from both sides all the way to a point. That's what I call flow equilibrium analysis, or it's also known as nodal analysis. But I go from that point of constant pressure, for that bound where I have a constant pressure, all the way to a place. And I suggest we have this equation, which was very ugly. I suggest we go all the way to before the choke to PWH, and all the way to the discharge of the choke. So you remember, if we go from here to here, we are going to make now a plot QG. Okay, and if we move from the here to here, the equation looks something like that, right? PWF, and that was my IPR equation. Now if I move to the wellhead pressure by including the other equation, right, and it will be basically QG and that's what one of your group mates, they wanted to derive this equation for gas. So you have QG so if you want to clear, what you want to get is how the wellhead pressure is going to look like versus rate. You want to group both equations in one. So basically you say QG divided by CT squared. Then you get minus PWF e to the S. Well, actually, that's not, should be the opposite. Okay, we want to substitute. We want to substitute PWF. And here I should have an E to the S someplace. Okay, my idea, my intention is to get rid of this PWF and just have PWH on that equation. One equation that just has rate and PWH. Okay, so I'd have to clear from here PWF. Yeah, PWH. This shouldn't go here. Okay, and then I substitute here. I have equation 1 and I have equation 2. Substitute 2 in 1. Okay, and I end up with QG okay, an equation that only I have a constant, a bunch of constants, and I have wellhead pressure and rate. And now you have to take a leap of faith. You have to make, you have to trust. But actually I say this equation looks exactly like this, but reduced. Okay, you can go and do the experiments at home. But actually looks like that, but looks a bit reduced. Why? Because when I'm losing pressure, right? The pressure I have here for one rate, I have certain pressure. But then when I travel to the wellhead, I have to deduct the pressure drop in the tubing, right? So the curve looks like the IPR, but scaled down. And this curve we call, all the way to that point, we call the available pressure at the wellhead. And available, why? Because I go with the direction of the flow all the way from the constant point of pressure, which is the reservoir, all the way to the wellhead. Okay, what happens when I have zero flow here? What pressure should I get here? I should have reservoir pressure minus the hydrostatic head of gas, right? So we have to substitute here on that equation 0. Okay, so then comes that PWH will be equal to this PR times ES. Okay, so if QG is equal to 0, then I have PR or PWH squared will be PR divided by E to the S.
QG squared versus the whole term?
Yeah, that's very correct. Should be like that. PR squared divided by S. That means remember, this S represents the hydrostatic head. Okay, so that means that I'm reducing that pressure. So now let's go on the other side. Now we are avoiding the choke. Okay, the choke is a guy which is complex. This guy is sensitive. Is complex. He's a serious guy. So we want now to move from here all the way to here. How that equation looks like? PDC. You remember the equation was QG PDC 0.5 times CFL. And here, so that equation, if I plot it, how it looks like, you can see that more clearly, right? Or not? Well, let's make an extra step. QG CFL squared PDC P separator plus okay, and then I take all of that 0.5. If you plot that equation, actually it will be like this, something like that, going up. What pressure do we have here at 0 rate if the pipe is horizontal? That's PDC, okay? PDC. That's PDC, and this one is P wellhead. What pressure do we get at 0 rate for PDC? simply separator pressure, right? But now if we want to increase the rate a rate greater than 0, that means I have to overcome the pressure losses in the pipe. That means that the pressure at the inlet has to be bigger than the separator. And if I use a higher rate, then I will have a higher pressure that I need at the inlet. Now let's assume for a moment, okay, there is no choke here. I have no choke in my system. If I put these elements, pipeline, reservoir, and flow line together, what rate should it produce? Well, actually, if there is no choke, right? So if there is no choke, then actually P wellhead will be very similar to PDC, right? That means the pressure, and here I'm looking at the pressure from two sides, from the reservoir side and from the separator side. But actually, the equation tells me, well, they should be the same. And what is the only place where they are the same? At the intersection here. So that will be QG is, people call it the equilibrium point if no choke. The producing rate is QG star. Now, what happens if we add, now let's think, okay, that's a simple case, there is no choke or the choke is fully open. What happens now if the choke, if I include the choke? Let's say I include it in PDC, in this curve. Does it change this point at all? If I include the, let's make it down, okay, because I think it's getting confusing. So you have the two equations, actually are where you had this curve, which was wellhead pressure, and this curve, which was PDC, right? And now I want to add to this curve. I want to make one that will be PDC, that will be PWH, that will be pipeline plus choke. That means I have, if I look at the system, it will be something like this. P separator, okay, and we can take exactly the same approach. You can try to clear, you can try, maybe you get a prize if you do the novel in, yeah, maybe not the novel, but you get something, a good prize. If you try to clear from that equation, what do you have to clear? PWPDC, right? And then you substitute that here on this equation. But what I say, let's make it more intuitively. What should happen if I have a choke now, okay? If I have no flow, doesn't matter. The pressure here should be equal to separator pressure. Now, if I increase the flow and the choke, I have a choke which is, you know, let's say 50% close. I have the original pressure drop, right? Let's say now I'm producing this rate. I have the original pressure drop, which came from here to here, plus an additional pressure drop due to the choke. Okay? Therefore, the curve will be shifted up like that. If I say P wellhead, and these are two in the same point, but this is wellhead seen from the reservoir, and this is seen from the separator, okay, with 50% open choke. Now if I make the choke 30% open, what will happen? I close even more the choke. Then the curve probably will add more pressure drop, right? And then I probably will have something like that. And at the same time, we have the same issue, right? We have both of them are looking at the same place. That's P wellhead, and here I have a pipe, the tubing, Okay, and I have my formation here. Okay, and I have P wellhead. They're actually in the same place. Therefore, the only feasible solution, if I put this system together, that's the only rate that I'm going to get for fully open choke. That's fully open choke. That's the rate I'm going to get if it's 50% open choke. And that's the rate I'm going to get if it's 30% open choke. Which also makes sense. When I close the choke, I'm reducing the equilibrium. Okay, the equilibrium is happening at a lower rate. Okay. That clear? Yes?
Is it supposed to be deviation or PDC?
That one is, yeah, this one should be PDC but for open choke. Okay, PDC, PWH for open choke. And that means that PDC is equal to P wellhead. Okay? Good. Now I say, when we go and proceed, we go to more complicated systems. We have oil, we have gas, we have multiple phases. These choke models, they become very, very complex. So I suggest using another approach, that is removing the choke completely of the system. So if you remove the choke completely, you have P, Q, and you have the two original curves, right? You have PDC, and you have P wellhead. What happens if I put no choke? This will be the equilibrium rate. That's the maximum my system can produce. If now I want to say, I want to produce this Q1, okay? What is, can I produce, the first question is, can I produce that rate? And the second question is, how? In that rate, let's go and cross on the curves, right? That rate, I have a lot of energy. I have a high pressure at the wellhead. But I really required, on the pipeline, a low pressure to flush against the separator. So if you see like that in terms of energy, I have more energy than what I need. So then I have to put an element to bridge and to bring down that energy all the way down here. So I have to put a choke that will be of that delta P, that provide me that delta P. Now if I say I want to be here, Q2, the same thing. Okay, I have more energy than what I need. Therefore, I have to create even a higher pressure drop. Therefore, the opening here is going to be, let's say, 80% or 50%, and here will be 30%, because I have to create a bigger pressure drop. Okay. Now that's okay. That's the whole point. What we were doing that is to say, in our calculation, right? This rate here. You remember what was the maximum rate that we can produce? What name did we put on that rate? Did we assign to that rate? The potential, right? In every reservoir pressure, I had a potential, which was the maximum rate that I can produce. In this case now, I have my potential. That's my production potential. But I can produce less than that. No problem, by choking. I just find a way, but I should be able to produce any rate below that. Okay, you see now the potential is not coming simply for substituting minimum pressure in the IPR equation, not from reservoir simulator, but now it's coming by taking into account the whole system, the whole intersection, all the system of equation. Okay, now what happens with time? Okay, that's another question. What happens with time? Okay, we are making exactly the same example, PWH and PDC. Okay. With time, which curve is changing? Okay, that curve, PDC, right? This curve is simply like that. So separator pressure typically doesn't change with time. If you go to a process engineer, tell him you want to change separator pressure, he's going to kill you or he's going to ban you. Okay? No way. And the flow line, it might change, right? Why the C of the flow line might change of the pipeline? If they replace it, right? They put a bigger pipe or a smaller pipe. If they have scaling, they have something growing inside the pipe. Okay, they have wax deposition, they have something that actually reduce the cross section of the pipe. In that case, that's affecting, reducing the diameter, and it's affecting the C. Okay, if you usually have scaling, it will be something like higher. Okay, you have a higher pressure. You need a higher pressure. But typically doesn't change with depletion. Okay, let's say I'm looking at the first 5 years, 6 years, that curve doesn't change, doesn't have anything inside of it that has any time effect. Now if we look at this curve, that one has something that is changing with time. That has this, which is very poorly written. Okay, we have some Schlumbergers trying to do some brainwash. Okay, so if you see that equation again, the same thing. Okay, here CT, maybe if you change the tubing, you have to change the curve. Maybe if you change the formation, how can you change the C of the formation? Make it more productive? Fracturing or acidizing? How can you make it, or how it can become less productive? You can have scaling, you can have plugging, you can have okay, you can have something that you can have coning, for example. Okay. But you have here this PR. And with depletion, this PR will go down with time. So what will happen is that curve with time, it will be going down due to depletion. PR1, PR2, and PR3. And PR1 is greater than PR2. So you see exactly the same trend that we saw before, right? That the potential, the exercise we have done in class, with time, if reservoir pressure is reduced, I had the maximum is simply going down. It's reduced. The maximum that I can produce from my system. Okay, QG, that will be 1, QG 2, and QG 3. How did we produce the field? How do we produce the field from the exercise in class? We produce it in plateau mode, right? We produce at a constant rate. So let's try to do the same with this figure. Let's say that our plateau rate, we have a single well, okay, which is not ideal, but let's say Q plateau. That's plateau. I want to produce this rate for as long as I can. And I'm now trying to predict for how long I will be able to produce that rate. At the initial time, right, you can see that I have more energy than what I need. Therefore, at time, let's say at time 1, reservoir pressure is 1. I need this delta P. I don't want to, well, I will spoil the graph anyhow. Okay, that will be delta P 1. Okay? You need the delta P choke 1. And then you say, yes, I can produce plateau rate, no problem, let's go to the next time step. Okay, you assume constant, you go to time 2, you calculate NP2, or in this case GP, cumulative gas production, and then you calculate PR2. Then you calculate this curve. And now you want to verify, am I still able to produce in plateau mode? And then I come and I check. Note that I'm in the same, on the same line. It's the same rate. The only thing now, my delta P2 will be smaller. What do I have to make operationally to make this work? Open the choke. Now I go to time 3. The same thing. GP3, PR3, and QP3, which will be this line here. Until unfortunately my line crosses below the rate that I want, and then no more plateau. I have to produce at potential. I have to produce at the flow equilibrium. So this is a way, without including the choke model, which is very ugly, that you can see how, what affects, you know, here we're not looking at the choke. The choke is something that is bringing these two down. Okay. So I think that's now before you take, well, we should take a break, and then you will have to make an exercise. Now, you know, we have a few quizzes in class. But what happens if, let's say you are here, okay, let's make a zoom on that situation. That's P wellhead and P DC. Okay. And I want to produce this rate, Q1 or Q plateau. You see here now the energy I have is lower than the energy that I need, or the pressure that I have is lower than the energy that I need. So what? I need to add energy to the system. How do I do that? Pump, in this case, is gas. Okay, so it's a compressor. So I have to add some element, not a choke. And that's part of what we are going to look at later. We have to put an element here, which is a compressor, that makes that bridge between the energy that I need and the energy that I have. So that will be the delta P of the compressor that I need. With depletion, if this curve continues to be going down, the delta P of the compressor will have the opposite effect. Every time will have to be bigger and bigger and bigger to match that difference.
When you reach a critical point where you can't run anymore, when you go, the graph goes to the left of the point.
Yeah, actually it happens something before that. Okay, something happens. So that's why I want to make this exercise. So one thing is that, for example, you see here I just need to find, that's the manager style. Okay, they say you just find a compressor for that delta P. Then comes the compressor guy and says, actually, I have no compressor that works for that. Maybe the delta P is too big, maybe the rate is too high, maybe the cost is too much. Okay, so that's the second part. It's not only enough to say that I just need that delta P, fix it. I just have also to be sure that the compressor I have can deliver this combination, because there are two things that are locked here, the delta P and also the rate. So I have to find an equipment that exactly gives me that particular combination of find a compressor that gives QG plateau and delta P compressor. And we're going to have an exercise on that. But now let's, so you decide, but I'm going to give you an exercise you have to make here in class. Now I'm checking if you understood. You told me yes, yes, but now we just want to check that actually you understood. Okay? So it should be very short. It should take you like half an hour, 20 minutes. But here is to practice exactly what we discussed here. And on top of that, you have the operational envelope of the choke, what we discussed here in class. Going up, and then you have constant. And you have it for constant inlet pressure, and you have it for different diameters. What is the effect of the opening of the choke on the delta P? Okay, so we are going to, you are going to do it, and then we check the solution here in class. And you can start whenever you want, but I just give, if you want to take a break in the meantime, but just pass it around. Okay? So use it, whatever. Yeah. You can do it in Excel, but just write the answers on the paper. Okay? Or you can do it on the paper directly. So let's say it's already 11:56. Let's say we try to resume back at 12:25. So we give some time for break and also for you to work on that. And if you're not ready yet, then let me know and we give some more time. But we come back 12:25. You volunteers. How did you get to the solution? Okay, that's fine. So what do you do? So just to be clear, we have a system. We are operating in plateau production. And we said we want a rate of 2.5. Okay, we had the conditions. We have made well testing. We know the diameter of the pipe. We know the elevation. We know the depth. We know everything else. And we know probably we will have a choke. Okay, so the task was just what is the choke pressure drop that you require to deliver that rate of 2.5. Okay.
Yeah. So we were given the constants and the reservoir pressure. So we first calculated the bottom hole flowing pressure.
Can you show us?
The equation to get the bottom hole flowing pressure.
Okay, so you took that equation.
Yes.
You had this and N and C, and you cleared
And
from
Q.
here
Yeah.
PW.
Yes.
Okay.
We calculate PWF.
So then you moved from here to here.
Yeah.
Co-current with the flow. Okay.
And then we use that PWF and we isolate it in the next equation. the
Sorry,
PV
what
equation.
pressure did you get there? Just maybe write it here and verify with everyone.
137. Around.
Okay.
It's good enough. And then we use that pressure in the tubing equation to get to all the constants. We calculate the wellhead pressure.
So you use the rate 2.5, 137,
Yep.
and then you clear that pressure here.
Yes.
Okay.
And then we got a pressure of 78 bar. Sorry, 74.2. No, 102.4. Sorry.
100 then?
102.4.
So, point?
0.4.
0.4. So, I ask you something. What could happen if... Could it happen on that equation that I don't get a solution? Is it possible that I don't get the solution? I get an error when
Yes.
evaluating that equation.
We got that first because we did something wrong. If you have a negative number in the square root, then you don't get a real solution.
Okay, when we calculate the available pressure, we are actually making PWF, PWH is the square root of PWF minus QG over CT squared. So it might happen, be careful that the rate that you are producing, just simply this will be negative, and then that doesn't exist, okay? And physically, what does it mean?
You can't produce at that rate.
Actually, if I want to produce this rate, maybe it's too big, I should increase this pressure, find a way to increase the pressure. Or make the CT maybe small, maybe bigger. If I make CT bigger, means bigger diameter, this becomes smaller, and then maybe I get positive number. Okay, next step.
Yeah.
Maybe another group. We ask someone else. Here in front.
Go to the next point. So we now have the wellhead pressure. Okay, now we need our inflow flow line, this pressure, so we get flow line wellhead separated. Just rearrange
From here to
from
here.
from here to here. Then we get our inlet pressure.
Okay.
And
So you
then
have here 40 bar, now
Yeah.
use here 2.5,
flow rate is the same.
and then you clear the
And then we can make we can calculate our drop difference.
What is that P in?
This is between wellhead and inlet.
Yeah.
There's the choke, and the difference between these two.
Yeah, the value here P in was
It was 74.2. Or
okay.
now you can calculate the pressure.
Could I have the same problem here? That I get a P, which is, I get an error, evaluation error, when for that pressure for P in. Yes.
No. There is no. Instead the
Because we have to, that's a very big difference, okay? We have, when we are calculating counter current, we get QG okay? Therefore, the thing that the term that I have under the square root is always going to be, usually it's always going to be positive. It might give you an unrealistic number, but still doesn't give you any error calculating. Okay, so be aware of that. Usually the computation errors of my models come when I go in the direction of the flow, and they are due because I don't have enough pressure basically to reach that point. On the required, usually that's not an issue. So that tells you that the ratio delta P of the choke is 28.2 214.
No, just 2 yeah.
Bar. Okay, we don't have this anymore. Just as a rule of thumb, okay, the critical flow occurs when P if I have, so critical flow rule of thumb, let's put it here. Critical flow occurs when we said P DC downstream of the choke divided by P wellhead is approximately 0.5 to 0.6. When I have, if it's that number or higher or lower, sorry, less or equal, okay, when it becomes if for example I have a big drop, this will become smaller, okay, then therefore this will be below 0.5 or 0.6. That's actually where I have critical flow at that point. So what is the pressure ratio we have? That will be P in divided by P wellhead. Just to have an idea what to expect. Okay, so probably should be on the subcritical regime. Now we come to the second part, in which I have the choke performance curve. That's what I call the choke performance. I have the dP across the choke, and I have also these are made for a constant inlet pressure. Is that similar to what we have? 102. Here we have 102. Okay. Now you have to be very careful. If this number was different from the number that you obtained, you cannot use this curve. You have to generate. Okay. You could only use it because it's for the same pressure. What happens when the pressure is higher, for example? Let's say I'm this rate, right? If I have a higher pressure, inlet pressure, should I get more delta P or less delta P? Well, you have to think about it. Okay. I'm going to give you the answer. But, okay, so we take the 2 points. So here we have for different openings, right? 40, 40, 42.5. And this I can make simply by changing that restriction. In a beam choke, I just simply replace the restriction by another with a smaller diameter. Or I simply regulate the opening of the choke. So the point we have is 2.5, the rate, the operational point that I desire, and the DP is like 28, so it's on that regime. Okay. From here on, here up, I have a critical flow. Okay, therefore I'm in the subcritical regime and I need some opening between 45 and 42.5. Okay, slightly closer to 45.
Excuse me. What's
Yeah.
the critical flow above that point?
Well, what is if we say it's 0.6, right? Let's say it's 0.6. So the delta P critical will be P wellhead minus PDC, and we know that P wellhead minus PDC is expressed as 0.6 P wellhead, and then we get 0.4 P wellhead, right? So I'm using this equation that I have here to clear PDC as a function of P wellhead, and then I'm summing both of them up 0.4. Our current wellhead pressure is 102. So that tells me the critical flow is how much is that? Yeah, like 40 something, okay? 48. No, 40.8. Okay. And you can also see it because simply the flow remains constant. At this point, simply doesn't change anymore. But just to get an estimate when that's going to happen, if you add your inlet pressure, you can use simply that equation. And that's actually 40 point something. Okay. Now, let's do a few before we leave this graph. What could happen if the point falls here? What is that meaning? If you go to your choke manufacturer, they propose this choke for that application. Okay, what do you tell them back?
The diameter is too large, so
I'm going to need, if my point falls here, okay, that means I'm going to need a bigger choke. Okay, I'm going to need a bigger opening. So they should provide just a bigger choke. If my point lies in here, okay, the choke is too big. I have to get a smaller choke. But always we are not going to, in choke is very flexible. Usually I can get bigger size, smaller size. I can be operating here or here. So I don't worry too much about if the point is feasible or not, if I can deliver that flow. When we come on the pump or the compressor, we are going to see the operational map is very restricted. So I cannot just take any combination and just be sure that I will find a pump. Okay, I will have to make sure that the point falls in the operational envelope. Okay, and then the last question was, how do we calculate the equilibrium? The potential, okay, that's what we say, the maximum that this system can deliver. We know it should be bigger than this 2.5, right? Because here I'm choking. If I open the choke, I should get higher rate. So how did you, let's say another group, no volunteers? Did you solve it for us?
I haven't been the last hour.
Okay. So you solved it? Yeah.
Yes.
Okay. So how did you solve it?
I assume that the PDC, the choke, and the well head pressure is the same.
Okay.
And I substitute the choke to the tubing equation.
You substitute this equation here,
Yeah.
and then okay.
Yeah. So I got the P choke squared to the tubing equation, and I got the rate.
And then did you use that equation? No? What rate did you get?
I get 3.3.
3.3? I don't think that's the right number, because you should include. Remember, we have to solve no choke, so I don't need any choke equation, but I have to solve this equation, and this equation simultaneously, all three. Okay? I should have here one unknown, two, then I have here, that's the same, these two are the same, so I have one more, and yes, so I have three unknowns and three equations. Okay. So anyone else, did you solve it manually or using Excel? Excel, okay. What number did you get for?
2.67 times fixed.
Okay, for open choke, QG is 2.67 e to the 6. And I think that's the result. You can do it by doing exactly the same procedure. Okay? You assume a rate, and then you calculate the delta P of the choke. When I'm in equilibrium, or when I'm at potential, the choke should be fully open. So then I assume a value, let's say bigger than 2.5, 2.6, calculate pressure here, calculate pressure here. Are they the same? Not yet. Then I change the rate once more, and then I compute until I find exactly 0 on the choke. Okay, I think now we can just one last comment before we finish, and then we have here Anga, for those of you who don't know him personally, our assistant. He's sitting here in the back, and he's going to give you some consultation time if you need for the exercise. But I just want to say that we don't have to calculate. Remember what was in the exercise we had. Okay, remember this exercise we had. On Excel. Yeah, before. Okay, in this exercise we have made, we had to calculate this potential, right? That was one of the steps. We want to calculate the potential, and then based on that, if it's greater than the rate we want to deliver, then we say yes, we can deliver that rate. If not, I have to reduce to the value of the potential, right? Now, if we include, in this case, this was a very simple operation to calculate that potential, right? It was basically simply to substitute in this equation. We just have to substitute PWF mean. Very simple operation. Now you see, it's becoming more and more complex. We will have to solve a system of equations to find that potential. And that's a very heavy operation. Okay? And if I start to include more wells, if I start to include more reservoirs, it's going to become difficult and more difficult to compute that potential. Okay, therefore, one approach you have is what we have discussed here in class. We assume that the rate is feasible on our system. Okay, we say we assume that it's feasible. The rate that I want, I come all the way to the choke, to the regulation element that I have, and I come countercurrent and co-current, and then I verify. If it's positive, it means I can produce. No calculating potential, anything. And that calculation is usually much simpler. I have no iteration. Simply I come, substitute in the equation, calculate that pressure, and substitute here, calculate that pressure. Finish. If you want to calculate, use the same approach, the potential, you need iteration. So then it takes a longer time. Okay. So then I wanted to say, I think there was some confusion on exercise 1. Just note that there is a typo. Here it should be maximum well rate. Okay. And essentially the maximum well rate is actually the plateau rate divided by the number of wells. Okay, simply like that. Because the maximum rate, you have it in the plateau period, and you divide simply by the number of wells you have. And that's, yeah. And there was one question. Oh, here there was another typo. Should be million. 8, 10, 20, 30 million standard cubic meter. That will give you a very long plateau. You will have a few generations just living from that field. Okay, and then we have these two optional questions that, and here, it's forced to make a short comment. So we said the production potential curve, okay, let's say CPP, production potential of the field, production potential of the field. We make a plot of that versus GP, okay, which is simply to say that we come on this column, we have the production potential of the field. So we plot this column versus this GP. That tells me, and remember why I put these two numbers together. This is rate, and this is the integral of rate. Okay, so it's like the same variable but integrated in time. Yeah. And that gives you a curve that, not to spoil anything, right? Any movie, but it should give you something like that. So if you take if you compare it with what we have done with the oil case, right? What have we done there to calculate plateau duration? We said the plateau will finish, the plateau period will finish is over when Q of the plateau is simply equal to the production potential of the field, right? Because at that point, if I continue producing more, I just simply have to reduce the rate. I cannot produce more than the plateau. So for TP, for T greater than TP, I produce that potential. And for T less than TP, I produce that plateau. Okay. So you can simply come with the plateau rate to this curve and read here the GP star. So that tells you at that GP is where my plateau will finish. After that GP, I'm going to be in decline. That means in decline, I always follow this curve. And before that, I will produce in plateau. The only thing in class for the oil reservoir, we could use the analytical equation. Okay, we could use. It was very simple. We just had to substitute. We simply came and substituted on the equation, and we found TP. Now you have to come to this curve, and you have to find this number somehow. It can be interpolating. If you have a collection of points, you can interpolate in those 2 points. You can add a trend line, and then you can use that equation to find that number. Okay. Now, the other question, which was also optional, is asking how can you use this curve? How can this curve be used for predicting post-plateau profile? And remember, after the plateau is finished, we are going to be producing at potential. The Q of the field is equal to the Q of the production potential. That means it's going to follow exactly this curve. Okay. So let's say I'm in a time T1. Okay, now let's say here I have plateau. That was T1. And then I go here and I have T2. And the only thing we know, this Q at 2 will be the production potential. Okay, but I don't know how much it will be. And here I have Q1. I know I can approximate how much was produced here by simply saying T2 minus T1, Q1 plus Q2 times 0.5. And here I say GP2 minus GP1. Right? This guy I have, these two I have fixed the step, right, to make it in a year. And this I have, but I have these two that I don't know how much I will, because this guy depends on this guy, Q2. Right? They are a function of each other. But you know that you are in potential. So if you have an equation for this one, that tells you Q potential of the field is a function of GP. Okay, you have that additional equation. Okay, so you can say this the iterative process is assume Q2, of course, has to be below the plateau. Okay, then I compute GP2. And after that, I calculate the potential, QPPF, with GP2, and then check if QPPF is equal to Q2. If it's not equal, then I have to again assume another Q. If it's equal, that means I have a solution. Okay, because the rate I should have at that particular time should always follow the potential curve. Okay, because I want to produce after the plateau, I want to produce as much as I can from the system. Okay, so that's a way that you can solve that. You have this equation with two unknowns, and then you know that you have this other equation that you should always be on that relationship. Okay, there are other ways. In the compendium there is actually another way, but you can use any way. Okay, so with that we close our session today. Thank you for coming, and we see each other next week on Thursday. Have a nice weekend.